So if D satisfies these three conditions, then D is called B metric on X, and pair X comma D is called B metric space with the coefficient X, with coefficient S. Sedgi et al. Proposed the concept of S metric space as follows. Let X be a non-empty set and S be mapping from x cube to non-negative real number. Satisfying these conditions, S of x y z equal to 0 if and only if x equal to y equal to z. S of x y z less than or equal to S of x x a plus S of y y a plus S of z z a for all x y z a belongs to x. Then S is called S metric. This function S is called S metric, and the pair x comma S is called S metric space. Soya et al. Combined the concept of B metric space and S metric space to introduce this new structure called SB metric space. Let X be a non-empty set. S greater than or equal to 1 be a given real number. A mapping SB from x cube to non-negative, the set of non-negative real numbers, is said to be SB metric on X if the following conditions are satisfied. First condition is SB of xyz equal to 0 if and only if x equal to y equal to z. Second condition is SB of xy equal to SB of y by x. And third condition is SB of xyz less than or equal to s time SB of xxa plus SB of YYA plus SB of ZZA for all XYZA belongs to X. Then SB is called SB metric, and the pair X comma SB is called an SB metric space. This is 5 minutes over. Okay, sir. So these are some examples of SB metric, and in SB metric, a sequence is said to be convergent if there exists Z belongs to X such that SB of x and Z tends to 0 as n tends to infinity. In this case, we write limit xn equal to Z. A sequence is said to be Cauchy sequence in SB metric space if SB of xm tends to 0 as n m tends to infinity. SB metric space is said to be complete if every Cauchy sequence in X converges to a point in X in the same space. So this is the definition of phi map. Let phi be the set of all functions small phi from non-negative reals to non-negative real. It is a non-decreasing function with these four properties. Then phi is referred as a phi map. This is example of phi map. And for this phi map, we have proved for the contractive condition of phi maps, we have proved this common fixed point theorems. So for proving the theorems, we require this definition. Let f comma g be self maps. If fx equal to gx for some x belongs to x, then x is called coincidence point of f and g, and w is called as point of coincidence. F and G are the self maps, then F and G are said to be weakly compatible if they commute at their coincidence point. And if this proposition tells us that if F and G are weakly compatible self maps, and if F and G are weakly compatible map on set X, and F and G have unique coincidence point, then that point of coincidence is unique common fixed point of F and G. This proposition is important for proving the result. So these are some main results. First result is let X comma SB be an SB metric space and F G be self maps satisfying this contractive condition where phi is phi map and k 0 less than or equal to k strictly less than 1 of 1s be a real number. Suppose the following conditions hold: f of x is contained in g of x, g of x is complete, then f and g have unique coincidence point. Moreover, if f and g are weakly compatible, then f and g have unique common fixed point in x. This is one of the important result, and this is corollary to that result, and this is the next corollary to that result. This is the next theorem. Let x SB be SB metric space and FGB self mappings satisfying this contractive condition where phi is a phi map and here SB of fx fy fz less than or equal to k times phi of m of gx gy gz where m of gx gy gz is maximum of SB gx gy gz SB of gx fx fx SB of gy gy fy SB of gz fz and phi is phi map and k is restricted to 0 to 1 by s greater than or equal to 1 and if f of x is contained in g of x is complete then f and g have unique coincidence point in x. Moreover, if f and g are weakly compatible then f and g have unique common fixed point in x. This is corollary to
So
the
your
last theorem.
8 minutes is
Uh,
over.
okay, sir. These are
9
the
minutes 10
references
seconds.
and thank you, sir.
Well, I liked your presentation. Is there any question from anyone? Anyone? Well, so I have just one question. Is that
Yes, sir.
like we all know that when we define a normal metric space between
Yes,
2
sir.
points, the distance when we define with dxy is a real number with some condition satisfied, then in our mind the interpretation is like that there is some abstract distance is there, right, between these 2 points, right?
Yes, sir.
Yeah.
Yes,
Can
sir.
I little bit understand when you talk about this B thing, but can you please tell me that when you are defining the S thing is on 3 elements, right? Instead of 2
Yeah,
elements.
yes, sir. Yes.
So
Yes,
do
sir.
you have some interpretation for that? Like, is that like from X, Y, Z, 3 points are there and you are adding the distances of X from X to Y and then Y to Z or something like that? Is there any interpretation in your mind?
Sir, actually, before S metric space, there was a G metric space, and G metric space represents means in usual metric space the interpretation is distance, and in G metric space the interpretation of that is related to area of the triangle, and like that.
Also, you are saying that when we are taking the 3 points X, Y, Z, then S X,
Yes.
Y, Z is a real number which approximately is showing the area bounded by the triangle made by these three points, right? Something like that you
Yes,
said.
sir. In G metric space, I am
Intimately,
just new to S metric space,
I understand.
but I have studied G metric space initially, and we are working in S and SB metric space right now.
But it makes
So
sense. It makes sense. So can you please go to the
yes, sir.
definition of S quickly for a few seconds?
Yes, sir. Yes, sir.
Yes.
This is the definition of S metric.
Can you please hold on?
Yes, sir.
I see. Yeah. Some modifications are there, I think, right? That other than the areas, I think some modifications is there.
Yes, sir. Yes, sir.
Anyway, like I like the presentation and I like the ideas as well. So it's a very good presentation. Thank you, Pramod Kumar.
Thank you, sir.
Yeah.
Thank you, sir. Thank you, sir.
With this, we do not have much time to discuss, though we understand that the topics are very interesting. But I have to call the next speaker, who is Ranjan Burman from Dinhata College. So it's over to you. Can you please share the screen and then start your presentation? Professor Ranjan Burman from Dinhata College. Are you there? I think he's not here. Well, then we call the next speaker, who is Reena from the Government College, Sector 9, Gurugram. Are you there?
Yes, sir.
Yes. Can you please share the screen and start your presentation? Reena Bhagavat, I think, right? From the Government College, Sector 9, Gurugram. Can you please start? Do it fast a bit. We are running out of time. Hello, Professor Reena, can you please start now, or you need some more time, then we can go to the next speaker. Oh, I think some network issue is there from her end. In that case, we may go to the next speaker, who is Kondekar Sachin Nagnath Rao from Diglur College, Diglur. Can you please start your presentation? Kondekar Sachin Nagnath Rao. Are you there? Am I audible? Presenter, can anyone please
Yes,
confirm?
yes, yes. You can audible. You are audible. Saurabh.
Okay.
আচ্ছা সৌরভ রঞ্জন বর্মন রঞ্জন বর্মন is absent.
So Ranjan Barman was there, I think, but then he left. I
Okay.
cannot see him now.
Okay.
Well, is Kondekar Sachin Nagnath Rao there? If not, then we can go to the next speaker, who is Shamir Kumar Bhandari from Bachkul Milani Mahavidyalaya.
I think he is also absent.
He's
You
also
can
absent.
call the next.
Well, okay, then we can go to Sufia Sabir from National Institute of Technology, Patna.
Yes, sir.
Okay, can you please share your screen and start your presentation?
Yes, sir.
Yes.
Sir, is it visible?
Yes, it's visible. We can hear you as well. You may start your lecture.
Okay. Thank you, sir. Good afternoon, everyone. My name is Sufia Sabir. I am a research scholar at NIT Patna working under the supervision of Dr. Ayaz Ahmed. Today, I am going to present my research article titled Numerical Solution of Fractional Order Burger Equation using Fractional Order Generalized Telescope Wavelet. These are the outlines of my today's presentation: introduction, literature survey, problem description, methodology, error estimation, numerical example, and conclusion. We first start with introduction. So fractional calculus, it is a generalization of classical calculus concerned with the operation of integration and differentiation of fractional order. The fractional derivative are non-local in nature, means the system remembers all its previous informations. FPDs are more fractional order partial differential equations or complex because of its non-local nature, singular kernel behavior, greater computational cost, and the lack of standard boundary condition. There are many numerical techniques for solving fractional FPDs, such as the finite difference, finite element method, wavelet-based method, fast algorithm. Research continues on finding high order and fast numerical techniques. Here we have, in this slide, we have presented some literature survey. We have listed some authors' name, the method used by them, their key contributions, the limitations of their method, and we have compared their method with our proposed method FOGCW. So the first one is Ray and Vera. They have used Haar wavelet method. Their key contribution is that Haar wavelet has a simple structure, but Haar wavelet is discontinuous and it is unsuitable for smooth fractional PDs. Our FOGCW works for smooth PD very well. Bhalekar and Daftardar used a fractional reduced differential transform method, but it is accurate only for a small time interval. Their limitation is they losses accuracy for long intervals. Our FOGCW maintains the accuracy over the large time intervals. Then Shen et al. Used fractional spectral Galerkin method. The key contribution of this method is that they achieved a high spectral accuracy, but the limitation is that it performance degrade for non-smooth behavior. Our FOGCW works also for non-smooth solutions. Then Saeed and Zaman used L1 finite difference scheme. Their key contribution is they have provided stability and convergency result for time-space fractional Burger model, but their accuracy decreases for high-order fractional PDs. Our FOGCW worked for high-order fractional PD as well. Bala et al. Used Legendre multi-wavelet method. The key contribution of this method is they have a good multi-resolution representation, but the limitation is that they need more number of basis function to give accurate solution. But our FOGCW give accurate solution using only a few number of basis function. So we have considered the following fractional order Burger equation defined by equation 1, subjected to two cases of initial and boundary condition. When alpha lies between 0 1, we have considered the initial and boundary condition of case 1, and when alpha lies between 1 and 2, we have considered the initial condition and boundary condition of case 2. Here we have defined some definitions, some basic definitions. A function gs is said to be in this space theta if we can find a real number zeta which is greater than it, and we can express this function gs in the form of s to the power zeta g0 s, where g0 is a continuous function. In the second definition, we have defined the Riemann-Leibniz fractional integral operator. So it is a convolution of the kernel s to the power alpha minus 1 and the function gs. In the next definition, we have defined the Caputo fractional derivative operator of order alpha. Then below we have defined some property of Caputo fractional derivative operator. Here we have defined the regularized beta functions, which is given by equation 6. Authors of 9 have proved the following lemma given in equation 7. So in this slide, we have defined some definitions of wavelet. So wavelet is a special type of function that is obtained by dilation and translation from the mother wavelet. When we continuously vary this dilation and translation parameter, we have this following family of continuous wavelet, which is given in the slide. Here we have defined fractional order generalized telescope wavelet. So the telescope wavelet on the interval 0 1 is given by the equation 8. Open substituting t equal to s upon h to the power alpha, we have the following expression for generalized fractional telescope wavelet, which is given by equation 9. Here rho bar m comma m denotes our fractional order telescope polynomial given by equation 10. So for the parameter k equal to 2, m equal to 4, alpha 0.5, and h equal to 1, we have the following 8 basis function for FOGCW. Here we have defined some properties of FOGCW. So authors of 9 have proved that this FOGCW are orthogonal on the interval 0h with respect to this weight function alpha t to the power alpha minus 1. In two-dimensional case, we have proved that it is the orthogonal with respect to the weight function alpha 1, alpha 2, s to the power alpha minus 1, and t to the power alpha 2 minus 1. In this slide, we have presented FOGCW in...
is over, Sophia. Okay.
Oh, okay, sir. Okay, sir. In two-dimensional case, we can represent FOGCW as follows. So this the FOGCW act as a basis for this space L2 0H1 cross 0H2. In this slide, we have presented the Riemann-Leibniz fractional integral operator of FOGCW. We have calculated the exact formulation of this Riemann-Leibniz fractional integral operator using regularized beta function. Here we have presented the function approximation in FOGCW. For any function UST, we can express this function in terms of FOGCW as follows. To find the approximate solution, we have truncated this series. We have taken M1 minus 1 order in S and M2 minus 1 order in T. Then we have the approximate solution UST given by the equation 11. We have taken the subsequent collocation point into the considerations. In this slide, we have presented the error analysis of our proposed approach. So authors of 10 have proved the following bounds. We have used this lemma and proved the next theorem. The statement of this theorem is that if the function FST belonging to L2 0H1 cross 0H2, and if this partial derivative exists and continuous on 0H1 cross 0H2, then we have the following upper bound for the L2 error. Now, to show the efficiency and accuracy of our proposed method, we have taken three numerical example. Our first example is given in equation 15, subjected to the following initial and boundary condition. So when we take alpha equal to 1 and mu lies between 1 to our problem 15 converted into space fraction PD, we have applied our FOGCW approach and solved this problem for different values of alpha 1, alpha 2 and mu, and we have taken k equal to 1 and m equal to 2. Then we find that our numerical solution exactly matches with our exact solutions. Here is the plot of our numerical solution and the plot of absolute error. From the second plot, we can see that we get zero absolute error. For the second example, we have considered this following fractional FPD subjected to the following initial and boundary condition of case 1. The exact solution of this problem is given by equation 18. In this table, we have compared our proposed approach with the method of 12 and 13 for values of alpha 0.99 and beta 0.1. In this slide, we have presented the plot of numerical and absolute error for nm equal to 8. For our third example, we have considered the initial and boundary condition of case 2. So the exact solution of this problem is given by equation 20. In this table, we have presented, compared our proposed approach with the method of 12 and 13. From this table, we can clearly see that our proposed approach worked very well in comparison of a method presented in 12 and 13. From figure, we can also see that our numerical plot and our absolute error for nm equal to 8. So these are the conclusions. So we have concluded in this slide. We have solved the fractional order Burger's equation by using fraction order generalized telescope wavelet. We have formulated the exact formulation of Riemann-Leibniz fractional integral operator using regularized beta functions that avoids numerical quadrature inside the basis operation and reduces approximation error. This RLFIO and together with the collocation method convert our proposed problem into a system of nonlinear algebraic equation. Then this system of nonlinear algebraic equation is solved by using Newton method. We have presented several numerical examples to show the efficiency of our proposed approach. Error analysis is also discussed, that establishing our proposed approach a highly promising tool for tackling complex fractional dynamics problem. These are some literature survey. Thank you.
Thank you, ma'am, for finishing it in time. Any question from anyone from the audience? Well, just one thing to ask, ma'am. What are the applications you just suggested now? In some medical field, you are going to apply it, right? You are saying?
Sir, Burger's equation application.
I
So it
see.
is applied in various fields, including fluid mechanics, gas dynamics.
I see. Yes. Okay. Well, thank you for finishing it in time. I don't have any other comment or a question. So by this, if anyone else do not have any more question, then we may go to the next speaker. Just one thing to inform everyone, that if some speaker is unable to present in their scheduled time due to the network issue, at the end we'll call all your names in the same order. So please, you do not leave this meeting. You stay here after the ending of all the scheduled presentations here. We will ask one by one to all of you who could not present in their scheduled slots due to some network issues. So please stay here. We'll come to you later. So by this, we call the next speaker, who is Miss Surya Banu R.
Yes,
from Wales Institute of Science, Technology and Advanced Studies.
yes, sir. Good evening, sir. Surya Banu.
Yes. Ma'am, can you please share your screen?
Yes, sir. Entire screen. Sir, did my screen is visible, sir?
Yes, absolutely.
Yeah,
You may
thank you, sir. Thank you so much, sir.
Yeah.
So I welcome you all for the.
You may close this screen, like where you can see us, or you may just, because it's at the middle of your presentation. So you may just remove it.
Which one, sir?
The one like by which you can see like all of us, the meeting link. Yes, this one. Can you please close it or no.
இல்ல வேணாம் brother.
Go to your slides.
Yeah, sir.
Yes. You may
Is
proceed.
it okay, sir?
Yes. Now you can see it properly.
Okay, sir. Thank you, sir. Yeah. Good evening, one and all present here. I welcome you all for this wonderful international conference on contemporary mathematical problems organized by the Department of Mathematics, Sitananda College, Nandigram, West Bengal. So my paper title is A Mathematical Review of the Fractal Graphs with the Simple Graphs. I am a full-time research scholar or Surya Bonu, Department of Mathematics, Vistas, under the guidance of Dr. R. Kamali, Assistant Professor, Mathematics Department from Vistas. So my abstract is fractals and graph theory are two significant mathematical domains that provide a powerful framework for analyzing complex, self-similar and highly connected systems. Graphs were used as models for analyzing a wide range of modern applications. Fractal applications were especially used in medical field and network communication system. This review highlights how fractal geometry and Euclidean geometry complement each other in both mathematical research and applied sciences. Introduction about fractals. Fractals have the self-similarity key property that is different at various scaling ratios. These fractals can occur in trees, lightning, birds, and feathers, and more in nature. This was invented by Benoit B. Mandelbrot in the year of 1975. Fractal applications are used in the field of computer networking, architecture, chemical sciences, and natural sciences. The Van-Koch curve is the best example of fractals. We can see the tree and the temple design. Then next one is introduction about graph theory. The study of relationship between structures of a graph is known as graph theory. This was introduced by the great mathematician Leonhard Euler in the year of 1736 with the Königsberg problem, which is where graph theory got its starts. Graph theory emerged as a separate branch of mathematics with this important contribution. Since then, the disciplines of computer science, biology, engineering, and cryptography have emerged. Applications of fractals. Area and applications connectivity role I have described. First one is nature modeling like rivers and tree, rivers and mountains. I can show the figure using self-similarity. This is a connectivity role. Then second one is medical imaging, blood vessels and brain tissues. Connectivity role is help us to detect a disease or abnormalities. The third one is the antenna design, fractal antenna in mobile and radar system. It is the connectivity role is to increase range and connectivity using self-similar structures. The last one is cryptography and data compression, fractal-based encryption and decryption. It is used to recursive connectivity to represent the data securely. The second part is applications of graph theory. First one is transportation networks, road, railways, flight routes. The connectivity role is used to ensure there is a path between all cities. The second one is internet communication, web links, computer network. It helps to detect walk lanes. The third one is biological network, that is neural connections and food chains to show how systems stay connected and balanced. The next part is fractal dimension. Fractal dimension is the most key eccentricity part of the fractals. The first example for this fractal dimension is contour set. Contours are the first one. We take a single line that can be divided into parts by parts. So here if that line can be divided, the scaling factor is s is equal to 3 for the first iteration. Here we can see the number of pieces is equal to n, that is capital N is equal to 2. The formula for calculating fractal dimension is log n by log r. The n denotes the number of self-similar copies. Then r is nothing but the scaling ratio. Here it is 2. The number of similar pieces is 2. Then scaling factor is 3. Therefore, log n log 2 by log 3 is approximately equivalent to 0.63. The fractal dimension of contour set is 0.63. The next example is Sierpinski triangle. For Sierpinski triangle, we should take a equilateral triangle. The equilateral triangle, in equilateral triangle, we have to mark the midpoint of each side. Then we have to draw a small inner triangle. So therefore, we can say the three shaded parts. Therefore, that n is equal to 3. The each line can be divided into two parts. Therefore, that is scaling factor, that r is equal to 2. So log n by log r is equal to 3 by log 3 by log 2. Therefore, the fractal dimension of Sierpinski triangle is 1.5. The third one is one coach curve. For one coach curve, we have to take the single line. It can be divided into like this. That line can be divided into four parts. Therefore, the length of the length generator will be defined as 4 by 3 for the second iteration. Third one is 16 by 9. Then the level 3 is 64 by 27. So like that, the fractal dimension is equal to log n by log r. Then we will get the answer is 1.261. So here I have defined some fractal polygon graphs. Already we know that what is graph. Graph is nothing but the collection of set of vertices and edges. But I have defined some more conditions with along with that graph. Then I can define this graph as a fractal polygon graph. The what are all the conditions? The conditions are nothing but the first condition, it should be a simply connected graph with p square vertices where p is greater than or equal to 3. The second condition is self similarity conditions. The third one is fractal dimension is 2. When the three conditions are satisfied along with the graph condition, that is the number of vertices and edges collections, then we can say that graph is a fractal polygon graph. I can give some example. The example 3.1. So a fractal polygon graph with alpha 2 is equal to 2. Alpha 2 is equal to 2 means that iteration that square can be divided into two parts. No, that alpha is equal to 2. Then example
Ma'am,
3.2.
your 5 minutes is over.
Okay, sir. Okay, sir. Thank you, sir. Thank you, sir. Then second example also alpha with alpha 4. Then for a fractal graph, I have given the cyclic graph. Then I have taken the another complement graph, acyclic graph. So this can be taken from fractal tree. We know tree. What is tree? It is acyclic graph. It has n minus 1 edges. But here I have added some more conditions, that a simple acyclic graph with 3p plus 1 vertices for all p belongs to n. Self similarity condition, second one. Third one is fractal dimension is 2. I had given the example with fractal tree with alpha 2 is equal to 2. I had given the next example, alpha 4 is equal to 4. Then I have given the theorem also. So every tree can be denoted as a bipartite graph. Here my fractal tree is also denoted as a bipartite graph. Bipartite graph means the number of vertices can be divided into two disjoint set. So no two adjacent vertices have the same color. Then it can be denoted as the two color. We can use only two color. So I can use two colors for my fractal tree. Therefore, it can be a bipartite. It can be a tree. It can be a bipartite graph. So example 3.5. Then according to all my conditions, I have concluded like that fractal graphs and simple graphs. Fractal graphs are modern invention. First one, simple graph is traditional method. Then number two, no specific size but specific scale is there. Self similarity structures also followed with the vertices and edges. Here the structure based on scale and specific size are maintained. This is the fractal graphs are appropriate for geometry in nature like a tree. Then simple graphs, it shows description of man-made object. Then fourth, the last condition is described by an algorithm for fractal graphs, described by a usual simple formula method. So conclusion, in this study, fractal graphs were discussed with the essential properties of graphs and fractals. This is a crystal clear theoretical approach for the fractal graphs. So mathematical approach is done with a related example to combine both simple graphs and fractal graphs. In future, the real-time applications will be discussed with these fractal graphs using rank nullity theorem. These are all my references, sir. Thank you.
Thank you very much, ma'am. This is a
Thank,
nice presentation.
thank you, sir. Thank you so much.
Is there any question from anyone? No question. Well, ma'am, just one thing. Can you please one more time show the slide where you talked about the fractal graphs first, like the definition?
Yeah, sir. I will show that, sir. Yeah. My first fractal polygon graph I have shown, sir.
Yes.
Yes, sir.
These PIs are the normal points, right? And this,
Yeah. PI is nothing but a collection of vertices, sir.
Yes, and
Yeah,
QIs are the edges there.
yeah, and collection of edges.
Right. And these squares you are making are called the fractals, right?
Yes, sir. Yes, sir. Along with these three conditions.
Okay. Yes, I
Yes,
understand.
sir. Yes, sir.
Excellent. Did you sometimes think to extend it to infinite graphs? Like,
Yes, sir. Yes, sir. It can be defined to infinity graphs, but with the conditions, along with the conditions, yeah, we can infinitely we can go along with these conditions, sir.
okay, so that will be like acted as the infinite fractal graphs, right?
Yes, sir. Yes, sir. I can conclude formula also for that, sir. Up to 8 iterations, sir.
I see. And then for
Yes.
the coloring, what you are doing? Like you are coloring these squares like
Yeah,
separately?
yeah. When we are coloring, what is meant by color? Color in a graph is nothing but we have to give the color
Mm.
no to, with the condition that is no two adjacent vertices have the same color.
Right.
Yeah,
But
that
then,
is called proper coloring.
but
Proper
I think
coloring.
that by the four coloring theorem, like you can say that every fractal graphs, finite graphs I'm talking about, that can be colored maximum by the four colors, right? I think
Yeah, maximum four colors, but
maximum.
fractal tree can be colored with two color only.
Oh
Fractal tree
yes,
I
that
can
was
color
your
two
that,
colors.
that was one of your main results, right?
Yes, sir. Yes, sir.
But then, like, I'm just trying to ask one thing. That's
Yeah,
why I asked all these questions before. That if you can extend this thing to an infinite fractal graphs and try to do the color the similar way as you were saying that two adjacent things like will not have the same color.
yeah, yeah.
How many colors do you need? Like, did you sometimes think about it? Like, or is there any
No,
result in the
for
literature?
for acyclic fractal graph, I can say, sir, with this minimum two color is required to color the graph. That's all. But a polygon graph, I have to check that, sir. But
No,
what you said,
the two colors it's for finite graphs, right? I think, but for
yeah,
infinite
for fractal tree,
for fractal tree, but which is finite, I think, in
yeah,
length.
yeah, yeah, sir, yes,
But
sir.
I'm asking that if you go for the infinite one, did you think, or is there any result in the literature that which talk about the how many colors you need to color them, like the fractal trees or the fractal graphs, if the tree is infinite or
Yeah,
the graph is infinite? I'm saying.
yeah,
Is there any
sir.
literature? Do you know that the
No,
number?
no, sir. I didn't know that. I have
Okay,
to
okay,
work on that.
okay. Yeah.
Okay.
So sometime maybe we'll see the result by your name. Thank you
Yeah,
very
yeah.
much. I liked your
Thank,
presentation very much.
thank you, sir. Thank you so much.
Okay. And
Thank you, sir.
well, by this, we are now going towards our next speaker, who is uh, Yogesh Nagar from Galgotias University, Greater Noida, UP, India. Dr. Yogesh, can you please come up and then share your screen? We cannot hear you. Can you please speak a bit so that we can check that it's okay? Hello? We can see your screen, but we cannot hear you. Can you please speak a bit? Dr. Yogesh Nagar, are you speaking? Some issue is there, I think. Are you speaking? Can you please write on the chat because your screen is already presented. So if you are facing some issue, you may take some time. We may go to the next speaker and then we may come back with all the speakers who could not give their presentation in their scheduled slots. Hello, Dr. Yogesh Nagar. Can you please write in the chat box that what problem you are facing? Well, okay, I think again there are some network issues. We may go to the next speaker in that case. And yeah, is there any chat there? Oh, we understand that we cannot hear your voice. I think that you may log out and log in again. Can you speak now? I think, yeah, can you make your sound a bit louder? We can hear you, but not that much. Can you speak a bit louder? Or make the volume? Yeah, you may go ahead. You may go ahead.
Okay. First of all, thank you for good afternoon, everyone. It is honor to speak of information content and conceptualizing problem here in Sitananda College. This is presentation. We explore the modern systems and classical approximation theory through short detailed theory of data and with thermal polynomial. This belongs to class ideas and continuity techniques to also study approximation of unbounded interval to create a constraint activity. These are the presentation arguments we will discuss in slide. However, what I need is to understand how these capabilities of the how effectively they actually transform our monitoring rate of when harnesses properly for frequency beyond formation. This paper
I request all the participants that if you are not presenting, kindly mute yourself so that we can hear a bit louder to him. It's already we cannot hear properly, so kindly mute yourself if you are not presenting.
any continuous function on a closed interval can be approached by polynomial with arbitrary accuracy. Later, the same polynomial will state the foundation with the elegant probabilistic construction now we known as the same polynomial, which offered a constructive proof of trace of a result. These following ideas laid the groundwork for the wide family of positive linear operators that form the platform for modern approximation. The modern application what began as a purely theoretical pursuit has now become central to various kinds of modern application. Approximation techniques support synthetic graphics, data fitting, geometrical modeling, numerical analysis, control theory, etc. Linear positive operators. Linear positive operators are crucial in approximation theory because we preserve positivity behaves predictive under the linearity, while the spin operator was beautiful on the bounded interval 0 to 1. They fail operate effectively on unbounded domain. Then Charles resolved this in 1950 by introducing an operator required with exponential weight design, especially enter half 0 to infinity. This innovation opened a new era of approximation on infinite interval and paved a way for numerous generalizations. The development of approximation theory can be viewed as the sequence of elegant milestone research initiated the field with uniform approximation was trained with the constrained probabilistic viewpoint saw the extended approximation to inverted interval through exponential weightage. Modern researchers enrich these ideas further through beta P type kernels, downstream modification, the Hermite trace extension. Together, these stages are tracing the evolution of classical theory into a rich contemporary landscape. Theoretical foundation. It, at its core, approximation theory is guided by cognoscible research theorem at continuous function can be approximated to any desired ratios using polynomial subsequent positive linear operator that mimics polynomial behavior that offer better spectral versatility. Such operator families provide a systematic and powerful framework for approximating function across diverse mathematical contexts. If we will discuss about the other operator, the definition of operator, the operator studying this work is created through a statistic blended and mathematical components are exponential weight data type integral kernels, Fourier parameters, and Hermite polynomials are the factors. Together they produce a flexible approximation mechanism suitable for measurable function on infinite intervals. The parameters are C, D, and alpha and I, and the operator control the operator's smoothness, shape, and convergency, giving researcher ability to fine tune its behavior. If we discuss about the momentum, these are the momentums which are related to Korotin theorem, which we are find. The others are find because we are reviewing these operators result. So these are the moments of this operator, and these are the analyzing. Number one is convergency and rate of approximation. In convergency, the authors analyze the Korotin type convergency, measures of smoothness, and convergence order. These Korotin theorem, using Korotin theorem,
Your 5 minutes is over.
these are the global approximations result of this operator, and these are the geometrical visualization which can clearly show that at different parameters scenario, it's approximately function, and this is the summary of our work. Operator construction and convergence property, state of convergence property. These are the related references which used in this developing this construction this operator. Thank you, sir. Any questions regarding this?
Yogesh, is it over like from your part, or you want to say something more?
No, sir. It is over from my side.
Yeah. So do you want to show some more slides? No. Okay. Any question from anyone? Well, I think that it was really very difficult to understand you. Your voice was almost non-audible. So, but the slides were interesting. I think that if we could hear you properly, it would be nice. But anyway, this is we have to accept it, the technical faults. I'm also not asking anything. But anyway, at some point in some other conference, I hope that we'll meet again, and then we may ask a few things in person. But by this, I have to invite the next speaker, who is Tirupati S., Wells University, Chennai. Tirupati S., are you there?
Yes, sir. Yes, sir. Yes, sir.
Yes.
There, sir.
Yes. Can you please share your screen and start presentation?
So my screen is visible, sir.
Yes, your screen is visible. You just show the PPT, and yeah, you are audible as well.
Yes, sir. Good evening to everyone, sir. I am Tirupati, research scholar under guidance of Dr. S. Meenakshi, Professor and Dean, Department of Mathematics, ISTAS, Chennai. My research title is Dichromatic and clique number of generalized Sperency graph S of G, T. Abstract. In this paper, study the central coloring theorem and structure parameters of the generalized Sperency graph S of G, T constructed from a base graph G and integer t greater than or equal to 1. The bichromatic number of pi of sg comma t and the clique number w omega of sg comma t. After recalling the regressive construction of s of g comma t, we first relate omega of sg comma t and omega of g and the layering structure induced by the Sierpinski operation, giving exact formulas in the several natural cases and tight bounds in general. Turning to B coloring, we derive lower and upper bounds of y of sg comma t in terms of classical invariance of maximum degree delta of g, clique number omega of g, and pi of g itself, and the regression depth in t. Our main contributes are exact evaluation of both omega and pi when g belongs to common families, uh, like complete graph, cycle graph, and path and certain regular graphs. Second one, constructive B coloring and achieve our lower bound of the broad classes, our base graphs, and matching upper bound showing tightness. And third one, structural characterization of these base graphs for the which pi of sg comma t attains extremal values relative to delta s of g comma t and omega of s of g comma t. Along the way, to introduce layering the domination framework that both simplifies the regressive analysis and beautiful and may useful for other coloring parameters on Sierpinski type of constructions. Examples and the computational experiments illustrate the sharpness of our results and suggest direction for further study, including least equipped value and B coloring of fractal-like families. Next one, introduction. Introduction. Coloring problems represent a cornerstone of graph theory, linking structural properties with combinatorial optimization. Among these, the clique number and bichromatic capture complementary features, maximum complete substructures, and strong color dominance constraint. The generalized Sierpinski graph S of g comma t is a t-fold regressive graph constructed from a base graph G. The class generalized classical fractal like graph such as Sierpinski gasket graph, H fractals, and mesh-based hierarchies. Next one, graph coloring. Definition of graph coloring. A proper coloring is an assignment of colors to the vertices of a graph so that no two adjacent vertices have the same color. A k coloring of a graph is a proper coloring involving a total of k colors. This is a graph coloring of some graphs. There is no two adjacent vertices have the same color. In the graph, only few colors are used. Next one is bichromatic number. The bichromatic number which is initiated Irving and Manlow in 1999. The parameter bichromatic number of a graph G is maximum number of colors for which has a B coloring such that every color contains a vertex adjacent to a vertex of every other color classes. Next one is the example of a bichromatic number. This one is a chromatic number. Chromatic number is the minimum number of coloring. Two. Next one, self-similar graph. A self-similar graph or shape consists of smaller copies of itself, appearing the same different scales of magnification. Copies of itself. The core features of is that object composed by smaller parts of identical copies of the whole. Scale invariance. The appearance of the graph or shape remains consistent regardless of the level of magnification. Next one, generalized Sierpinski graph S of g comma t. Based on the base graph, the vertex set is V of g. S of g comma t is constructed for the integer t greater than or equal to 1. Each level introduce V of g copies of S of g comma t minus 1. Edge connected corresponding vertices according to structure of G. Next one, the generalized Sierpinski graph denoted by S of g comma t is a regressive graph construction based on the given base of graph and positive integer t. Let g of v comma e be a simple connected graph if with v equal to 1 to etc n vertices. Then the generalized Sierpinski graph is defined as the vertex set v of s g comma t equal to u1 etc ut. u1 belongs to v of g. I lies between 1 to t. All the length of sequence made vertices, the edge set is to vertices of x1 equal to u etc t, y equal to v1 to t, the adjacent s of g comma t if and only if their conditions I such that uj equal to vj, ui and vj are adjacent in G, uj equal to vi, uj equal to vi for all j greater than 1. This is
Your
the
5 minutes is over.
Yes, sir. Thank you, sir. Self-similar graph or definition of self-similar graph. Chromatic number of generalized Sierpinski graph. This is a chromatic number of this graph is 3. B chromatic number of generalized Sierpinski graph is 4. This is applied for 4 classes. They used only 4 colors. The green color is adjacent to every other color classes. B chromatic number of generalized Sierpinski graph S of G, 1. Dominance condition depend on I degree vertices. In S of G, T, degrees vary widely depending on the position of coordinate where adjacency occurs. Degree of the corresponding vertex in G. The degree of G of V equal to degree of V. Then the vertex set V1, V2, Vt in Sg of T. D of S equal to summation of degree of graph of Vi, n less than Ti minus 1. Hence, the I degree vertices G produce extremely dominant vertices of upper levels. Upper bound, the pi of G less than or equal to delta G plus 1 and delta of S of Gt grows exponentially in T. The upper bound of pi of Sg, T less than or equal to delta of S of G, T plus 1. The properties of Sierpinski graph, number of vertices V of S, T is equal to number of vertices in V of G. The G is connected, then G, T is also connected. Degree depends upon the degree of vertices in G. Regressive structure, S of G, T is equal to union of SV of G, T minus 1. Each SVG, T is copy labeled of with prefix V. Since every B coloring is proper coloring, therefore the bounds of B chromatic number is chromatic pi of G, psi of G less than or equal to pi of G less than or equal to delta of G plus 1. Clique number is omega of S, G, T. The clique number of indicates the size of largest complete cyclic subgraph. For any connected graph G and T greater than or equal to 1, omega of Sg, T equal to omega of G. In complete graph, omega of S of G, T equal to n. In a tree, omega of Sg, equal to 2. The result in for many families of G, the B chromatic number of stabilized, if G is deregular with D greater than or equal to, for all T greater than or equal to 2, then pi of Sg, T equal to degree plus 1. In complete graph, pi of G equal to n. In Sierpinski graph with k vertices, S of k n, T is n regular, each level of, therefore pi of S, k n, T equal to n. In a cycle graph, Cn equal to greater than or equal to 4, therefore pi of G equal to 3. Pi of Cn, T equal to 3 for all greater than T equal to 2. 3 is pi of G equal to delta of G plus 1 in many cases. Then pi of S of T, T is typically equals pi of T. Applications, fractal modeling in networks, graph coloring studies in B chromatic number, regressive and similar in network section, topological and combinatorial graph theory. Conclusion, in this article examine the clique number and B chromatic number of generalized Sierpinski graph S of G, T. Main conclusions are clique number remains invariant. Omega of S of G, T equal to omega of G. B chromatic number is bounded, but any increases pi of S, G, T greater than or equal to pi of G with exact equality for many regular and classical graph families. Sierpinski regression enhances dominance properties but not complete adjacency. These results provide the foundation for exploring chromatic properties and regressively constructed networks. Then these are the references, sir. Thank you, sir.
Thank you, Tirupati Rajkumar. Any question from the audience? Just one thing, Tirupati.
Yes, sir.
I want to ask that this B chromatic number, did you define it? Like, did you introduce it, or it
Already done, sir. Already done in complete graph, bipartite graph, path graph, by newly introduced in Sierpinski graph.
You have introduced it, right?
Yes, sir. Yes, sir. Yes, sir.
Oh,
Yes,
good,
sir.
good.
Yes, sir.
Good. I like your presentation, but we do not have much time to discuss on that.
Yes, sir.
But with this, thank you. Thank you for your presentation, but we have to move on to the next speaker then.
Okay, sir. Thank you, sir.
Okay.
Thank you, sir.
Well, so as we have written here that our next speaker is Krishna Gopal Pradhan, from Ramnagar College, Ramnagar, Purbo Medinipur. Can you please? Yes, we can see your screen. Can you please speak a bit so that we can hear you? Krishna Gopal Pradhan, we cannot hear you yet. We cannot hear you. So can you please speak?
Yes, now you hear?
Yes, it's yes.
Okay,
Now
thank
it's
you, sir.
audible. Yeah, you start.
Good evening to all, and I am Krishna Gopal Pradhan from Ramnagar College, Assistant Professor of Mathematics. So here I will present. The screen is visible, sir.
Yes, yes, it is visible.
Okay. So my paper title is Left Annihilator of Identities with Derivation. Mostly I cover in this presentation introduction and brief history, aim of research, motivation, main results. First of all, we define few class of rings here. A ring R is called a prime ring if whenever A or B equals to 0 for A, B belongs to R implies either A equals to 0 or B equals to 0. This is a definition of prime ring, and then we generalize this class of rings like this. A ring R is called a semi-prime ring if whenever A or A equals to 0 for A belongs to R implies A equals to 0. So by definition, we can conclude that every prime ring is a semi-prime ring, but converse is not true. Well, we define some function on this type of ring. Let R be a ring. A map F from R to R is called an additive map on R if f of x plus y equals to f of x plus f of y for all xy belongs to R. An additive map D from R to R is called a derivation on R if d of xy equals to d of x into y plus x into dy for all xy belongs to R. More definition. Let R be a ring xy belongs to R. The element xy minus yx is called commutator of x and y, which is denoted by in the third bracket x comma y. We define more like this. This we call kth commutator. Kth commutator of xy for k belongs to n naught inductively as follows. We set zeroth commutator of x and y as a x, and first commutator of x and y is the commutator itself, and then inductively we can define kth commutator with the commutator of k minus 1 commutator of x and y for k greater than 1. These type of identities are called in this literature angel type identity. So first of all, history of investigation. Study of derivation became popular in 1957 when Posner EC established a result concerning the relation between the structure of prime ring and structure of special additive mappings defined on the ring. Posner proved in this paper, the paper is cited below the slide, if D is a derivation of R satisfying a relation like commutator of D of x and x belongs to center of the ring. ZR represents the center of the ring here. So for all x belongs to R, then either D is 0 or R is commutative. So he proved this result. After that, many researchers generalized this result. So aim of this type of research and in this area of research is there are so many interest growing in this research area. Here we study mainly commutativity of prime or semi-prime rings. The main objective of the work is to investigate some functional identities satisfied on a suitable subset of prime or semi-prime ring, and then to determine the structure of the rings or the associative associated function. Sometimes we get the function in a simple linear form, or the base ring is become commutative if that holds some certain type of identities. So motivation of this paper, in 1978, Hastings proved that for a prime ring R, if characteristic of R not equals to 2 and R admits a non-zero derivation D on R such that a commutator of D of X and D of Y equals to 0 for all xy belongs to R, then R is commutative. For semi-prime ring R, Bell and Diff proved in their paper that a non-zero right ideal I of R is central if the commutator of D of X and D of Y equals to X and Y for all xy belongs to I.
Dr. Pradhan, your 5 minutes is over.
Okay, thank you, sir. I will finish it now. So further, Huang proved the following. Let R be a prime ring with a derivation D, I a non-zero ideal of R and Mn fixed natural number. If the identities, that is nth power of D of the commutator of X and Y equals to nth commutator of X and Y for all xy belongs to I, then R is commutative. Or if characteristic of R not equals to 2 and the nth commutator of D of X and D of Y equals to nth power of X and Y for all xy belongs to I, then R is commutative. So in this paper, we have generalized these two identities. So we have taken annihilating condition of these two type of identities, that is left multiplying by some non-zero element A, or if we remove the non-zero condition, then we will get either it is 0 or something else we get in the result. So we have taken the identities presented in the screen, and we dropped the characteristic condition on the previous result. So main results in this paper is let R be a prime ring, I a non-zero ideal of R, and 0 A be a non-zero element in the ring R. Suppose that D is a derivation of R and n and m fixed integers greater than or equals to 1, such that A into nth commutator of D of X and D of Y minus nth power of X, commutator X and Y equals to 0 for all xy belongs to I, then R is commutative. In the theorem 2, we have proved that if R is prime ring, I a non-zero ideal of R, and D a derivation satisfying the another identity, then the R is commutative. And also we have studied the result for non-commutative semi-prime ring. Here, if left Utumi quotient ring of R and C is the extended centroid of R, D is a derivation of R, and A belongs to R. If any of these following two identities, then there exists a central idempotent element E belongs to U, such that the subring EU is commutative and 1 minus E into A is 0. We can generalize this result further by taking generalized derivation, which is not introduced in this slide, in this presentation, but we can generalize this result furthermore. So thank you.
Thank you very much, sir. It was a nice presentation.
Yes, thank you, sir.
Anyone wants to ask any question? Any quick question? I think that we are very much running out of time, and sorry, sir, I cannot ask you, or we cannot discuss anything now, because we are really out of time. So with this, I thank one more time to Professor Krishna Gopal Pradhan, and we are now going to the next speaker, Priyanka from Agurchand Manmal Jain College.
Yes, sir, I'm here. Sir, is my screen visible?
Yes, yes, your screen is visible.
Good evening, sir. Myself, Priyanka, assistant professor, research scholar, and one second, sir.
It's not visible anymore.
Now, sir?
Yes, it's visible. Yeah, you may minimize it or close it. Yes,
Ah.
this one, this bar.
Okay, sir.
You may close it as well if you want.
Okay.
Yeah.
My research topic is decision making under deep uncertainty, a generalized neutosophic assignment model with multi-criteria, multi-expert evaluation. The following slides outline the contents of my presentation from abstract, introduction, motivation, contribution, preliminary, methodology, declassification, and experimental results, conclusion, and references. Abstract. Assignment problems are key in resource allocation, scheduling, and logistics. Traditional methods fail with uncertain or conflicting data, especially from multiple experts. Our approach introduces a novel aggregator that merges truth, indeterminacy, and falsity values from all experts and criteria. This ensures a unified, reliable decision for each task work pairing. The method supports better handling of uncertainty and diverse expert opinions in multi-criteria environments. Introduction. An assignment problem underpins critical domains like resource allocation and scheduling, requiring optimal tasks to aid in matching under multiple criteria. Classical and fuzzy assignment methods inaccurately handle uncertainty, contradiction, and indeterminacy in complex relevant data. Neutosophic fuzzy logic, with its triadic structure, offers a superior framework to model such multifaceted uncertainty. Despite its promise, neutosophic fuzzy assignment has been underexplored, particularly for multi-expert, multi-criteria contexts involving conflicting or incomplete information. Motivation. Existing methodologies fail to robustly integrate heterogeneous, uncertain, and contradictory data from multiple experts and criteria. There is a pressing need for frameworks that effectively model and aggregate truth, indeterminacy, and falsity in assignment decision making. Bridging this gap is crucial for improving accuracy and reliability in assignment problems reflecting of real-world complexity. Contribution. Propose a novel multi-expert, multi-criteria neutosophic fuzzy assignment framework utilizing single-value neutosophic set to encapsulate threefold uncertainty dimension. Develop a custom aggregation operator that synthesizes triple membership values from diverse expert and criteria into a unified decision matrix. Introduce a defuzzification strategy to transforming neutosophic fuzzy data into crisp assignment matrix suitable for classical optimization algorithm. Validate the framework via synthetic and practical case studies demonstrating superior performance over conventional fuzzy and intuitive models in managing conflict and indeterminacy. Preliminaries. A single-valued Fatih neutrotropic set A on universe U is defined by membership function Ta of x, Ia of x, Fa of x belongs to 0, 1, subject to 0 less than or equal to Ta of x plus Ia of x plus Fa of x less than or equal to 3. For assignment problem, each pair ij can have a neutrophobic cause Cij equal to Tij, Iij, and Fij. Neutrophobic assignment problem. A neutrophobic assignment problem aims to find an optimal allocation between two sets under uncertain evaluation represented by neutrophobic numbers. Mathematically, the goal is to maximize the total score. Max is equal to Z. Max Z is equal to summation I is equal to 1 to n, summation j is equal to 1 to n, Sij, Xij, subject to summation I is equal to 1 to n, Xij is equal to 1, summation j is equal to 1 to n, Xij equal to 1, where Xij belongs to 0, 1. The proposed generalized framework extends this formulation to multi-expert, multi-criteria, and generalized neutosophic environments, thereby capturing deep layers of uncertainty and complexity. Proposed methodology. We propose a comprehensive framework to address the assignment problem within a multi-expert, multi-criteria, nutrosophic context. The approach comprises three integral parts: the aggregation of the nutrosophic assignment, the defactification of the synthesized data, the application of a classical optimization technique to derive optimal assignment. Proposed methodology. Data model. Assume M expert each evaluate a set of K criteria for the work task per IJ. Each expert K yields Cij over KL is equal to Tij KL, Iij KL, Fij KL, where L is equal to 1 to K indices criteria. A goal is to unify these into a single nutrosophic cost. Assume a set with N workers, N tasks, M experts, and K evaluation criteria. Each expert K provides a nutrosophic evaluation for each work task pair under each criterion L, denoted by Cijkl is equal to Tijkl, Iijkl, Fijkl, for Ij is equal to 1 to n, and K is equal to 1 to m. Our objective is to synthesize all evaluation for each IK pair into a unified nutrosophic cost. To consolidate evaluation, we propose the following aggregation strategy. This aggregation ensures averaging 2 degrees to capture consequences across evaluation, conservatively taking the maximum of indeterminacy and falsity to reflect worst-case uncertainty. Remark: if Tij plus Iij plus Fij is greater than 0, normalization is applied proportionally to preserve nutrosophic validity. To enable classical optimization, the nutrosophic triples are defactified into a crisp cost value using a linear weighted function. Cij is equal to alpha 1 minus Tij plus beta Iij plus gamma Fij with alpha beta gamma greater than 0. The larger Tij means lower cost, while bigger Fij and Iij and Fij penalizes the assignment. Experimental result. Here, we are evaluating which worker fits which task using input from several expert and criteria. Instead of giving a single score, each expert provides a nutrosophic fuzzy triple. Since we have more than one expert and more than one criterion, each pair accumulates several such triples. We combine these into single aggregated triple for each work task combination. Each task runner. If any of these triple exceeds a total of 1, we scale it proportionally to maintain consistency. To use these
Your 1 minute is over.
okay, so I'll finish it up. To use these values into optimization, we convert all triple into one numeric cost through the falsification step. We use simple weighted scoring function that penalizes lack of truth, uncertainty, and falsity with the weight 0, 0.7, 0.1, and 0.2 respectively. This gives us a single cost value for each work task assignment. Within this cost matrix, we can then apply the Hungarian algorithm to identify the optimal assignment. The algorithm systematically evaluates all possibilities and selects the combination within the maximum overall cost. The optimal allocation we obtained is worker 1 assigned to the task 3, worker 2 assigned to task 2, as worker 3 assigned to task 1. This assignment results in the lowest total cost equal to 0, 1, making it the most efficient matching based on all expert evaluation and criteria. Conclusion. Fuzzy assignment is designed to model uncertainty with partial membership but failed under high contradiction and new defalsification errors. Multiple expert fuzzy assignment extended to include expert opinion yet struggled to unify conflicting judgments. Multi-criteria fuzzy assignment handled multiple performance metric but flattered when criteria conflicted. Multi-expert and multi-criteria fuzzy assignment combined expert diversity and criteria complexity but couldn't resolve contradictions or incomplete data. Intrasystic fuzzy assignment incorporated membership and non-membership but lacked true modeling of indeterminacy. Nutrosophic fuzzy assignment introduced truth, indetermination, falsity to address deeper uncertainty and inconsistency. Multiple expert nutrosophic assignment effectively aggregated diverse expert opinion using triple membership value. Multi-criteria nutrosophic assignment captured conflicting criteria with enhanced clarity and decision accuracy. Multi-expert and multi-criteria nutrosophic assignment unified both expert and criteria inputs into a reliable, conflict-resilient, and decision framework. The proposed nutrosophic assignment framework offers a robust solution for assigning problems with multi-expert, multi-criteria, and uncertain data outperforming traditional fuzzy methods. It is particularly effective in handling incomplete or ambiguous information. Future work may express scalability, high expert weighting, and real-time adaptability. And these are my references. Thank you, sir.
Thank you. Priyanka. Any quick question from anyone? Just I want to ask one question very quick. Like the second last slide, I think that you talked about some intuitionistic fuzzy assignment.
Yes, sir.
Is it connected to some hating algebras or something? Like, you know
Sorry,
that?
sir?
Is it connected to some hating algebra or something like what is intuitionistic fuzzy assignment thing?
Fuzzy assignment problems capture membership values, truth membership values, where intuitionistic fuzzy assignment capture truth and falsity membership value. When coming to neutosophic, we can also take into consideration indeterminacy membership values at the different.
Right. That
That's
means
the difference. Yes, sir.
some hating algebra is involved there. Yeah.
Yes,
So
sir.
that was my answer. That it should be that the belongingness thing should contain some other value than 1 and 0.
Yes,
Right,
sir.
which
Yes, sir.
you are saying the indeterministic thing.
Yeah.
So that means some hating algebra is involved there.
Yes, sir.
Anyway, so we don't have much time. So thank
Okay.
you very much for your lecture. So
Thank you, sir.
we go to the next speaker. So we start again, going back at the beginning. The speakers who could not speak in their scheduled slot, now we are starting with them. So the first speaker is Dr. B.S. Anitha. Can you please share your screen from?
Yes, sir.
Yes. So at the beginning, some problem was there.
Yes, sir. Now only sharing.
Yes, it's clear now. We can hear you properly. We can see your screen as well.
Okay, sir.
Please go ahead.
Good afternoon, myself. Good afternoon, sir. Myself, Dr. Anitha B.S. I'm working as assistant professor in Rajareshwar College of Engineering at Bangalore. I'm going to present my paper entitled on Lorentzian beta Kenmodes manifolds. Okay, first we have to. In this paper, I can be divided into 6 groups. First is we have to discuss about the introduction. Okay, introduction in there. Okay, this one is equal to. In the Sassakin manifold was introduced, studied the Procel and the W2 curvature of the P Sassakin and the Kenmos manifold. Okay, after that 1972 K Kenmos manifold. Okay, Kenmos manifold, the condition satisfies f of t is equal to s into e power t is the non-constant, and along with the Vepron product I into multiplication product of the n on interval. Okay, we call it as a Kenmos manifold. Currently, we are in distinguish between. Okay, we have to find out in the here W2 curvature is equal to 0. The condition in the B Kenmot manifold. After that, we will discussing their Bochner curvature, Valley conformal curvature tensor and Valley conformal curvature, and this one is equal to conformal curvature tensor. Next, we have to go to the discussion about the basic concept. Basic concepts of the Lorentzian beta Kenmode manifold. In the Lorentzian beta Kenmode manifold, we have to put the conditions. Basic properties we have to sharing there. Okay, these are the basic properties. Okay, next we have to Lorentzian alpha beta equation conditions. Okay, Riemannian manifold with the W2 curvature center is equal to condition. We have to take the 0. After that, we are using the conditions Bochner curvature. Before that, the curvature is constant. When the hyperbolic curvature constant is equal to -1 is there. -1. After that, we have to applying the condition C Bochner curvature. After some properties of the conditions, we have to existing their curvature. We will get finally 1 to hyperbolic constant function is equal to -1. It existing the W2 curvature tensor is equal to 0. Okay, suppose it is not existing, we will not find out in any solution. After that, we will go to the conversation. Okay, what we are getting their result is Einstein manifold or is not Einstein manifold. When the Einstein manifold is satisfying the relation, okay, Ricci tensor is equal to the Riemannian curvature tensor is equal to 0. Okay, whatever they are getting the constant, we will equal to the some other standard error is existing. Suppose it is not existing, the conditions is equal to 0. Okay, we'll find out in the error, we can't find out in there. Conclusion of this, the matrix of the Riemannian manifolds and the Ricky tensor. Okay, suppose we are adding any different types of curvature and the manifold. You have to admitting with the W2 curvatures, tensors in their manifold. Is it possible to do it? Okay, is existing their manifold or not existing their manifold? I'm using only the C positional curvature and Bailey conformal curvature and Bailey projective curvature tensors. These are the conditions I'm using. Okay, it is existing only the Einstein manifold. It is not existing only the Nita Einstein manifold, sir. These are the I'm working in this paper, sir. Thank you, sir.
Oh, well, so any question from anyone? So you have finished, right?
Yes, sir. Yes, sir.
Yeah. Any question from anyone? Well, Dr. Anita, you did not show any result.
Yeah, but it is not moving, sir. That is the main problem. Slides is not moving.
Well, can you please drag that
I'm also
sidebar?
trying to drag also. Drag is also not working though.
Okay. Okay. So you are well.
Yes, sir.
So is it something that you have submitted this paper somewhere, or
No,
did
sir,
you?
not yet submitted, sir. Just I prepared only for that, for conference.
For this conference, right?
Yes, yes, sir.
Okay. So okay, I understand. Anyway, so it would be better if we could see the results a bit, then we could discuss a bit, if though we do not have much time, but now in this scenario, it's almost impossible to discuss. But anyway, I think if it is needed, that the organizers will ask for your paper, and then will take the decision. But anyway, I'm now going to the next speaker, who is Professor Ranjan Burman. Can you please come up and share from Dinhata College? Dr. Ranjan Burman from Dinhata College, are you there? If not, then Dr. Reena Bhagat, can you please come up and present your slides?
Yes, sir.
Yes. Can you please do it a bit faster so we are running out of time? Yes, we can see your slide now. So can you start? Yes.
Thank you, sir.
Yes.
So I'm Reena from Government College Sector 9. My paper topic is on the structure of non-uniform wavelet in Sobolev space. This paper presents a study on the construction of non-uniform multi-resolution analysis in Sobolev spaces, and this will establish a corresponding density condition. Furthermore, the study extends to the construction of non-uniform wavelets in Sobolev spaces. The relationship between filters and their construction is also explored in this paper. These findings contribute significantly to the field of multi-resolution analysis and wavelet theory. So, first, I will give the definition of a Sobolev space because I am working on this space. So here is the definition of Sobolev space. For any real number s, the Sobolev space SSRD consists of tempered distribution functions such that their norm is defined like this, and in the where dot is taken as in the Euclidean norm, and the corresponding inner product is defined as like this, where 1 plus mod of xi square to the power s, this is a weight function. Now, next is the definition of spectral pair, which we have used in our theorems of this paper. In this paper, so definition of spectral pair: let n greater than 1 be a given integer, and r be an odd integer, which are relatively prime, such that r lies between 1 to 2 and -1. We consider the translation set as 0 r by n plus 2z, where z is a set of integers and our L is 0 and 1. So this translation set is not necessarily a group or a uniform discrete set. So basically we are working on a non-uniform vector space. So this here this spectrum for the spectral set, and this pair is known as the spectral pair. Now, the basic classical definition of MRA uh, uh, is already defined, but we have modified this classical basic definition of multi-resolution analysis for the space of Sobolev space. Given an integer n greater than 1 and odd integer r with the condition such that r and l, they are relatively prime, an associated non-uniform multi-resolution analysis is a collection of Vj of closed subspaces of HSR and satisfying the following properties. First one is the nested property. Second one is the density condition, and closeness condition, and third one is the density condition. And now the fourth one, this D condition is important, because when we are in the Sobolev space, so the weight function, due to the weight function, and this space is not a dilation variant subspaces. So for this space we have to define our scaling function at each scale. So for the this phi j, where belongs to Vj, such that this collection is an orthonormal system for Vj. So this is a very very important definition for our theorems. So we have modified the classical basic definition to this definition. Now this is the main theorem of our paper. Let n be and this is known as the orthonormality condition of multi-resolution analysis in the Sobolev space. Let n is greater than equal to 1 be a positive integer, and r lies between r belongs to 1 to 2 and -1 be an odd integer. Now we are writing this gamma and this capital gamma rn like this. If s is a real number and phi j belongs to the Sobolev space where j is an integer, then we have the condition first for each fixed r, this distribution are orthonormal in the Sobolev space if and only if these two conditions are satisfied. If these two conditions satisfy, then we can say that this satisfies the condition of orthonormality, and these are the if and only if conditions. Next, in this theorem, in this theorem, we have the two conditions for the orthonormality of this distribution. We have two conditions, and in the next theorem, we have combined these two condition in a single condition. In this theorem, the result is like this: the distribution phi j lambda are an orthonormal in the Sobolev space for every odd integer, if and only if this condition satisfies. Now, next is the density condition of a non-uniform multi-resolution analysis in the Sobolev space. Let phi j belongs to z be a sequence of elements in HSR such that for every j, this distribution are orthonormal in the Sobolev space. If Pj is the orthonormal projection from HSR onto the space of Vj, then for every f belongs in HSR, we have this condition equal to 0. Moreover, if there are the condition when a and that alpha is greater than 0, such that their integration condition is less than equal to capital A for every j less than equal to 0, then integration j equal to minus infinity to infinity Vj equal to singleton 0. Then this is the density condition of a non-uniform multi-resolution analysis. Now next is the scaling relation.
Ma'am, your 5 minute is over.
Okay, thank you, sir. The following scaling relation, this is the scaling relation. When we are in a scaling relation, when we are taking the Fourier from the both of the side, then the left hand side becomes this and the right hand side becomes this, and the coefficient, this coefficient m naught j plus 1 to n to the power minus j minus 1 xi, this is a filter. This we call filter, where phi j is like this m naught j plus 1 xi. So basically this is the coefficient of the Fourier transform, where m naught this is locally in L2 space, and since this is spectral pair, we can write our filters in this form: m naught j plus 1 equal to m naught 0 1 plus exponential to the power this. So where m naught 0 1 and 0 2, they are locally L2 half periodic functions. These filters satisfy the following conditions. So first we were doing our definitions on the functions. Now we are implement our theorems in the form of filters. So the first theorem, which is based on the filters, if phi is in the Sobolev space, which is satisfying the theorem 1, then the filter m naught j in 1 satisfies this condition, and this condition also. So this is the next theorem, which is based on completely on our filters. Thank you. These are the references of my paper.
Thank you, madam, for finishing it in time. Any question from the audience? Anyone want to ask anything? Okay, thank you. I think that we are very late. I am not going to ask any question or any comment. Thank you again for your presentation. And we are going to the next speaker.
Thank you so much, sir.
Yeah, we're going to the next speaker, who is Dr. Kondekar Sachin Nagnath Rao. Are you there, sir? Dr. Kondekar? Well, if he's not there, I think that we have covered everyone, and there is no other professors remaining in the list for the presentation. So I think that we have covered everybody. We have called everyone. Is there anyone left in the list? No. Okay. If not, then I'm straight away going to Professor Dipanjana. So you may conclude the session with the organization talk.
Thank you. Thank you, Saurabh for giving us your precious time for this slot. Thank you. Thanks again. We can touch with later. মানে আমরা পরে যোগাযোগে থাকবো. Okay. So thank you all participants for this nice talk, for their nice talk. So here we can here we conclude this session, and we can go to the next session, the validatory session. So every participants are requested to join the program link for the validatory session. Thank you. Thank you.
Just before we end, Devanjana, if you allow me, I can just say one line to all the participants who are still present here.
Okay.
That for their presentation, like what I felt today, that see that there are few presenters who are like the senior professors, senior lecturers in some colleges, and there are some participants who are actually doing their PhD or postdoc. But the main thing is, what I am trying to share is that for 10 minutes presentation, you see that there are many speakers, as I've said, that who has presented their topics properly. But for the maximum number of speakers, what I just want to, just as a suggestion, I want to say one line, that for this kind of very short presentation of 10 minutes, what we as a presenter, as a mathematician, we should keep something in mind, that our papers are like very difficult. Like for 1 year or 2 years, you are working in one thing, and then in 10 minutes you are presenting that. So it's difficult for you. It's difficult for the audience as well, right? So always what we should do, that you give your 4 to 5 minutes to explain the basics first, that what are the basic definition, the basic. And after that, just speak for the next 2-3 minutes, one statement of your work, which you consider as the main statement. That's all. Like that should be a presentation, because we do not have much time. So from the next time is my suggestion that if you are facing this kind of short presentation, that spend your time 5 minutes, 6 minutes for explaining the basics, and then just talk about only one statement. That's all. This is a good presentation, can be considered. What is happening that we are like in 30 seconds finishing the definitions and all the basic things, and then trying to say the statements. Who are going to understand the statements? Because the basics are not understood. So this is a problem. So this as a suggestion that from your next presentations, short presentations, you may keep these things in your mind. Thank you very much. That's the only thing I wanted to say.
Saurabh,
Yes.
there is a participant in the chat box, Nilambo Tripathi. He said that his name is not called yet, but I think he missed his name because
Nilambor Tripathi.
the serial number is 6.
Did you call him Nilambor Tripathi?
Yes, you called before, but he missed his call. That's
So
why.
Nilambor, are you ready with your presentation? Professor Nilambor Tripathi.
Yes, sir.
With your presentation?
Yes, sir.
You may go ahead. You may do it. Devandana, I think that we should give some time to him.
Okay. And very quickly, you can.
Yes. You conclude very quickly. Okay. Go ahead.
Just,
In 4 to 5 minutes, you finish it.
Yes.
So whether I'm audible? Hello.
Yes.
You are audible, but your screen is not visible. It's a white screen.
Sir, I already shared the screen.
No. Yes. It's now shared properly. Now you go to the PPT and present it.
Oh, okay, sir. Sir, is it visible?
No. Yes. Now you go to your PPT only. Minimize this screen and go to your PPT. Minimize this. Do not close.
Yes, sir.
Yes. Now
Yes.
you go to your PPT.
Is it sir clear? Is it sir visible, sir?
No. I think you did not share the entire screen.
Yes, sir. I have already shared.
No. Stop sharing and share the entire screen. First, go to the present option. Then select entire screen, not only window. You first stop sharing. Stop sharing this one.
Yes, sir.
Okay. Now you go to the present thing and go to entire
screen
screen.
share.
First, click on entire screen. Then select the option next and click on share. Single click, not double click. First click on present, then click on entire screen, then select the screen below and then click on share. What's the problem, Nilambar?
Sir, actually the screen is not sharing.
Time is over. Time is running. There is a validity session also, so you can hurry up.
Number, you go to the share screen option first at the bottom. Just beside the video symbol, you have a share screen button, right?
Yes, sir. Yes, sir. Yes, sir.
Click there.
Then window.
Then, no, not window.
Entire screen.
Entire screen.
Yes,
Then
sir.
select the screen option below. Then share. Do not double click, single click. Single click on enter.
Yes, sir.
Click
I'm
on enter
using.
screen, then select it, then share.
I've already
Click
said
on
it's.
share. You clicked on enter screen. Did you? Yes, I think it worked now. Yes, now you go to your PPT. Yes.
Is it visible, sir?
Now. Yes. Go and finish it in 5 minutes.
Okay. Sorry for the late, sir. My name is Nilambar Tripathi. Today I'll present my research on Grady based in Ollie sequence space, focusing on their geometry challenge and new direction in approximation theory. These are my outlines. In the Grady based and fundamental in actual Grady based are fundamental in approximation theory, especially in LP space.
You do not have to show the outline. You just go to the definition and show the main result. That's all.
Okay, sir. These are my definitions. Usually in what is Grady base? The Grady base an Ollie sequence space LM is defined by a convex function, a basis Grady if the thresholding Grady algorithm expresses any vector optimally, almost Grady bases relax unconditionally, requiring only quasi-gradness and democracy. The delta 2 conditions control the growth and affect the existence of Grady bases. The geometry of Ollie spaces is like the geometry of LM is captured by the fundamental function phi. When M satisfies the delta 2 condition, the space behaves like LP and the unit vector basis in democratic. Without delta 2, gaps appears in phi, breaking the democracy and the making unconditionally Grady bases impossible. Then in classical LP spaces, the unit vector basis is always Grady. Ollie spaces differ because growth of M can be irregular, causing norm of characteristics vector to fluctuate. This non-homogeneity requires new approach to construct Grady type bases. The main results usually the criteria of thinking linking the Q convexity, R concavity, and the uniform convexity to the Grady bases, construction of conditional almost Grady bases via gliding home techniques, tensor product behaviors, and many more. We provide the thresholding. We provide simple criteria for when a basis LM is Grady. For spaces without delta 2, we construct conditional almost Grady bases using the gliding home technique. We study tensor products showing Gradiness is preserved only under the homogeneity growth conditions. And the key structures to identify the gap between gap in the phi n build looks sk in the gap and concentrate them. This ensures that Grady approximation select entire blocks, controlling the residual and giving almost Grady behaviors. Conditionally constraints satisfy the km log n, and these are the properties which are used in here. And one of my result is also write a result that is the reflexive of Ollie's function in when it does not satisfy delta 2 conditions. Actually, these are the results which we used here. And I have already proved give one of the result without the delta 2 conditions. And these are my conclusions. Solid space have richer richer structure than LP. Grady West depend on the delta 2 convexity and modular growth. Conditionally almost Grady bases even exist even when unconditional one fails. Opens avenues in spheres approximation and machine learning. And these are my references. Here. Thank you.
Thank you, Nilambar, for finishing it in 5 minutes. But definitely, we do not have time for any question or any comment.
That's why completing in within the stipulated time.
Okay. Thank you. It's over to you, Devangana.
And thank you, Saurabh. So we can conclude here in the third session, and we can go the validatory session by using the main program link. All are requested to join there. Okay, Saurabh, bye.
Okay. Bye bye.
Bye bye. Thank you very much.
Welcome. You're welcome. Okay.